So then let's start. Our first speaker, invited talk by Biró Tamás from the Wigner Research Centre for Physics in Hungary. And Biró will talk about dynamical growth and reset models for income distributions. So please, Professor Tamás.
Thank you. Good morning, everybody. Of course, I feel also extremely pity I can't be in Kolozsvár right now in such a beautiful day, but as we all know, this pandemic situation forces us to practice virtual conferences. So I think the two important points in this title, I should explain what is LGGR stands for, and then at the end I shall also show you some mathematical speculations about how to characterize income and wealth distributions. So the LGGR is just an abbreviation you see on the top line. This is a local growth global reset model, which is a special kind of Markovian random models. So
Professor Biró, sorry, maybe you can share your screen.
Oh, I forgot to share my screen. Oh, sorry. Let me get to this share screen. Share. Is it working now?
Yes, we can see the desktop.
No, I have a problem because no, I don't. Ah, my God. Why is it so big? Right.
When you share,
the problem, I don't reach my other slides.
When you share screen, you have the two options to share the desktop or to share an application. So you could share just your PDF or whatever or your PowerPoint, whatever you have.
Okay, how can I share that?
Maybe you just go out and now you go to the share and see what you want to share.
No. If I put on this share, I'm sorry, then the whole screen is occupied by...
No, you can select what you want to share.
Okay. So desktop one, whiteboard, what is whiteboard?
No, don't share the whiteboard. Just find your presentation. Where is your presentation there?
Okay. But then I don't have the Zoom window if I have my presentation. That's the problem.
You will have. Just open it and open the Zoom window over it. And then...
How can I do that? That's a problem because it always comes to the top what I opened the last. So this is a crazy technique. I'm sorry.
You should figure out. It should work. It should be no problem, I think. So
okay.
If you...
I try
it again.
I can't. Oh my gosh, no. What if I share this?
Let's see.
Okay.
This is just the desktop, or...
Is it okay now?
No, this is the desktop that we see. We don't.
But why don't you see what I see on the desktop?
You should select what you want to share.
But how? Where to select? That's my
open. Where is your PowerPoint? Start it with your PowerPoint.
It's a PDF viewer.
PDF. Open your PDF.
It's open.
Okay, and then press this share screen down there.
I think he has to go out of the share again.
Yeah, so just leave share.
What do you see now?
The desktop. Okay, great. Oh. You have it.
I'm sorry, so did too. It was good to start a few minutes before the time. Thank you. I'm sorry, this Zoom is a little alien.
Okay, great.
So
you're online.
LGGR model is an abbreviation for local growth global reset, which is a special class of Markovian models. And I shall talk about this in more details coming. So this is when you are not symmetric like in diffusion, you can go up and down to the left and the right in small steps. We assume you go in one direction only, let's say it's the only Gros in a Markov chain, but rarely a very big step back to the starting position, what we call reset to the ground state. And this kind of model we applied not only to income distribution, but also to a number of other phenomena. And this has the advantage of its simplicity that you can find a number of analytic solutions. And then after reviewing this and some data we gathered about income distributions in the late decade in the Cluj County, I shall also talk about a mathematical construction related to the Gini index, which expresses the inequality measure of this income and wealth distributions. Okay, let's go on. LGGR. So here you see on the left some schematic views. The usual more diffusion-like Markov model, when in an abstract state space, you can make small local jumps to go to a neighboring state, but in both directions. And this is like a one-dimensional diffusion. From the n, we index it, you can go to n+1 and n-1. In the middle, you see the LGGR, which is a special type of that. You can go from n to n+1. This is the local Gros with a given rate in the model. And from any state, you can go to the 0, which is the ground state. And this is then the global reset. And just the third column shows you an even more general process when you can have partial resets as well. That's typical for earthquake models when both small and big jumps are balancing each other or not balancing each other, depending whether you are in a stationary state or not. So this is the schematics of the model. So here you see it in equation 1, that is the discrete version of a kind of, well, I don't call it Fokker-Planck, but this is the master equation to this LGGR model, only for n bigger 0. First of all, the change in the state n can be fed from the state below, from n-1, can be consumed by going to the n+1, and also consumed by going to the 0 state. And only the 0 state has a feeding from all of the others, and then it is a sum, which is just the expectation value of the rate. The rate gamma is for the reset, depending on the state. It can be state dependent, and the rate mu is the Gros rate, which is local. And this equation 2 is its continuous version. And then you see here is no second derivative in x, but mu and gamma can be x dependent, and the expectation value through an integral is coupled back to the differential equations. Such simple systems can be solved analytically. Here in the table, I just show you a few examples. And it is interesting that the simplest assumptions lead to the most frequent examples. So for example, if both rates are constant, independent of the state, then we have in the continuous version and also in the discrete version an exponential stationary state, which we call Qn or Qx. That state is stationary when the time derivative, partial time derivative is just 0. And then this is a first order problem, very easy to solve. The next, if the growth rate depends on the state, and this is what you might call is a preferential growth, the more you have, the higher rate you even increase, or the more connections you have in a network, the higher the rate that you can have a new connection. And if this is the linear, the mu of x is a linear function, then what you get in the continuous version is the so-called Salis-Pareto distribution. I am going to show you the very formula for that. And there is a discrete version of it, which is also known as distribution from failure statistics, for example. And there are a lot of others. It's interesting, for the Gaussian stationary solution, we would need a constant growth rate and a linearly growing reset rate. You shall see why it is so. So how can the growth rate be established or modeled or even measured? So in the ideal situation, of course, we have access to data. We can model the Q of X stationary distribution, and we can recheck and have some access on the growth rates and the reset rates. So the model building means that you decide what is your mu and growth rate, and then you decide what is your reset rate, and then you solve, and then you compare with real world data. So of course, just that can be constant, can be linear. This is the rich gets richer principle. The more you have, the more probable that you have an increase even more. And you can use for different assumptions here in different models. For the income distribution, we are going to use this linear preference growth rate. What about the reset rate? The reset rate can be, of course, a constant. When this is independent how much you have the same possibility to lose it all. This is more like for gambling models. Another interesting realization of this, which is related to the citation distributions, if you have a sample space, let's say the big N, index small n is the number of cases when you exactly have n units of something, be it money, be it citations, be it something else. And then its change is just simply described by the growth rate, but the sum of the all is also growing. So that makes a dilution in the sample space, and the fraction what you have, the probability, will have this gamma effect. And if this is just exactly exponential, then the gamma is same for all stages. Then you have an exponential dilution, and then you get a constant gamma. So this is the other very common mechanism to consider a constant gamma. And of course, if you have a decay of n elements in the state n, and each element independently has a rate, then it would be linear, and so on. Also, maybe interesting to note that mathematically it will be very important to have the limit when the gamma is much smaller than the mu, if the resets, the catastrophes, are very rare. Okay, so what are the properties of this model? It will be just a short list. Of course, this term, which occurs only for the evolution of a ground state probability, it just ensures the normalization. So in the practice, you can solve for all the rest and then calculate the probability from the normalization in the ground state. This is of the type of the processes which are linear in the probability, this master equation. And then you have a matrix for a possible transition from any state to any other state. And then we specified it just having a local growth rate here from n-1 to n, and have a global reset rate. And then this is, and all the theorems, all the results you have for this type of master equations also applies for the LGGR model. So it approaches, then it is proven that the entropy is growing, and it approaches the stationary distribution and with any definition of the entropic distance, which uses a convex trace formula. If you have questions on that, we can talk about this part. Now, the continuous version is much simpler to solve analytically than the discrete version. Also, you can have very nice solutions also in the discrete versions. So let's see now, come to that. So here some results. First, how this LGGR works if we have constant rates. So the stationary distribution you can obtain is exponential in the n, and then the coefficient depends on these both rates. And then you can see that if gamma, if it's very rare, the reset, then this is just gamma over mu is here, the coefficient to the n. This is a kind of beta in the thermodynamical Boltzmann-Gibbs distribution. Having the stationary distribution, you might be interested how you approach it. So if we define the difference from the stationary distribution at any time, we can derive also analytically in this case that the approach is about exponential. And then this is a convolution with the Poisson distribution defined by the Gros rate. This is just a mathematical result, but it ensures you for any positive gamma, this difference will diminish after enough time. So it's nice to consider the stationary distribution. In the case of continuous models, it's better to look at the ratio of the actual distribution to the stationary one. And then you find out that the evolution looks like a kind of soliton. So the solution at any time of this ratio at any value x is just the initial shape shifted. And this is a kind of Galilei shift in this case. Now let's look at the linear preference, because it is also very frequent in the praxis and we very much interested. First of all, in this case, the stationary distribution has a power law tail for the big N. And it also, you can derive analytically that there is an exponential supremum of the approach to the stationary distribution. In the continuous case for the ratio, I just show you a glimpse of this derivation. Then the ratio evolves according to this equation 5. It looks like fluid dynamics if you ever solved hydrodynamical systems. And in case of 1 + 1 dimension, one time and one variable, this can be solved nicely analytically, and the result is just an integral of the exponential of the integral of gamma over mu factor and some kind of Jacobian factor comparison of the Gros rates. And that is. So let's look some data. How does it fit to data, and what do the data suggest to us? What use for mu and gamma as a model? So this is again just a graphical picture of the LGGR model. Another one what we like. So you go up, up, up on the chain, and sometimes you go back, up, 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 and sometimes you go back. And this can have a balance. Oh, this is now a version of that, but for the income, you not only remove people from the ensemble, let's say going to pension, to retire. Retiring is typically at the higher incomes. So then the gammas are going in the direction of reset, getting out from the scheme. But at low income, there are entries. And the starting salary can be smaller or bigger, but bigger with smaller probability. So usually we expect here intuitively a scheme when the gammas both come in and go out, can be positive and negative in the equation, and then the chain goes up. And this is the model of income evolution. Let's get to data. This data was an average of decade 2003, I think, to 2012. And this is from Cluj country in Romania. Here you see on the horizontal axis an income in the local currency. And here you see the growth rate, which you look from the data, so year by year, and to take the difference. And we found it so nicely linear that we cannot have another continuous model than just mu x is sigma times x. This is linear. The linearity constant is about 1/5 in these units. The reset rate is here more complex. It's not constant. It looks like constant for the higher income levels, a constant leave with different incomes in different years, but it looks that it is rather the opposite. It's negative for small x. So what we have fitted here to the data, blue points, is a gamma minus b over x type of formula. It's more or less okay. Let's calculate with this. And here are data for different years. And this is the probability density function, the rho. And then you see it does not look very much uniform. They differ from year to year. Of course, there was inflation. There were some changes in the world economy, in the local economy. So they don't look like one curve. But if we plot it as a function of x over the x average, and we assume this scaling, then you see all these different year data come to a common curve. And this common curve with the assumed mu and gamma rates, it just led us approximately, this is to this stationary distribution. As you know, this is a version of the beta distribution. It looks like a Pareto tail, because if x is big, it's about x to the minus 4. It's a power law tail distribution, but at small x, it also can rise. It looks it would have some maximum. So that was then the result of the mu and gamma, and it seems that this LGGR model successfully predicted a stationary distribution. We also tried to compare this, how universal is this distribution, to some data from other countries. By some countries we had success, by some other countries less success, or even some enigmatic changes. We don't know yet the answer why. It probably can be difference on how people collect income data, from whom they collect income data. Yeah, it is also the taxated income, of course, in this case. But you see some of them, like Russia, comes closer to this Romania fitted line. Hungary is at the low income is different at the higher income, but all at the large income follows almost the same line. The brown ones are from the original where we fitted the rates, and here you see that what comes. So if you allow me now, in the rest of the time, I have some 9 to 10 minutes, I would like to show you a more mathematical speculation about the Gini index related and the suggestion to look for a quantity by calculating the Gini index, which has properties, behaves very much reminding us to the entropy properties, and that's the thing what we find. So the definition of Gini index is equation 8. You look for differences in the income, but the absolute value of differences, you make this double average with the distribution, and you compare it with the 1/2 times the 1 over average you multiply. So it can be understood, this division. It puts the Gini index between 0 and 1, between 0 and 100%. But it's nice to use here cumulative, tail cumulative distributions. So this cumulative integral is the fraction of wealthy people having income or wealth above the quantity x, and the f bar is just the the wealth possessed by them compared to the average income. So both are fractions between 0 and 1. How can they be calculated? You can look for numbers and then you can make divisions. What is interesting is the Pareto bon mot, and Pareto is famous about his 80-20 rule, which says that 20% of the population, C bar P equal 20%, has the 80% of the wealth. So we call anything Pareto point when C bar is P, F bar is 1 minus P, which means P fraction owns the 1 minus P fraction of the total wealth. The Gini index can be then expressed like a simple expectation value of something, and this something we would like to call then Gintropy. Maybe because of time, please allow me to jump over here a few derivations. We can come back to that if there is any question, and I show you curves. So the one is the Lorentz curve, when this cumulative fraction of wealth against cumulative fraction of population is plotted. Here, the main diagonal is the equality line. You have the rich end at infinite, continuously infinite wealth, and at 0 wealth, the other end. And all the Lorentz curves are above these lines, and the Gini index half is just the area, what you see here. And if you have the other diagonal, which is the P1 minus P, the Pareto point is just when they meet. So there are, and what we call Gintropy is the difference of this Lorentz curve to the equality line. And this is always positive, as you see from here, that we can also prove very simply. This is a never negative quantity. This is exactly maximal at the average income. And what is even more interesting, for some very known distributions, it looks like a formula for entropy density. So examples, of course, if you have only one possible distribution, you have only the equality line. If you have two distributions, then you already have a Gini index and you have a square window of Gintropy as a function of the cumulative population. And you can have a window for the probability distribution, and then the Gintropy looks like a parabola. And if that distribution is exponential, you just get a kind of Boltzmann formula for this Gintropy. And if this is Pareto and the end, what you get for the Gintropy is the suggestion trace formula for the Tsallis entropy. So here is this table, again, just a summary. Here we have for exponential distribution, we call it natural, the Gibbs distribution. We have the Boltzmann formula for this quantity Gintropy, and the Gini index is exactly just 1/2. And here you have some other interesting formulas which all occur in other physical systems. So here again, just the Gintropy curves to compare the Lorentz curves on the left side, the Gintropy curves on the right side. They are very much look like binary entropy curves, as you see. And some are symmetric. One is symmetric for the echo window. Some are not symmetric, and they look like that. So let me summarize because time is going. We have presented the local Gros global reset model, having a big advantage that it's analytically solvable in several cases, and in the most interesting cases, the most simplest assumptions about the rate in this Markovian model lead to very, very frequently met stationary distributions. The constant rates to the Boltzmann-Gibbs, which is the classical thermodynamics equilibrium distribution, the linear preference in the Gros rate to the Tsallis Pareto, which is also very popular and very often discovered in income and wealth distributions, or some versions of it. we tested this model on real world income data. And at the end, I presented you a few formulas to view at the inequality Gini index, which can be related to entropy-like formulas. And the Gini index would be just the expectation value of this entropy-like quantity. We call it gentropy. This we constructed as a mule word from Gini and entropy, so you understand. So thank you for your attention. What shall I now do with my push and escape?
No, just leave it open
Okay.
for questions. Thank you very much for this very interesting talk. Actually, I learned a lot also, which I can use for my research.
Oh.
So we have plenty of time for questions. So don't be shy that to ask questions. Either now, since we have so much time, you can just maybe open your micro and start talking, or you can formulate your question into the chat. So while we're waiting, let me start. I have 2 or 3 questions of my own.
Oh.
I didn't understand the issue of the approaching the stationary state with solitones. So maybe I missed the point there. Solitones, well, are defined that they are not shaping shape. So how can you approach a stationary distribution when you have solitonic dynamics? Because solitones, well, they keep their shape.
Yes.
I missed the point here.
Where it is, let me come to that. Here, for example. So it is not the distribution itself, which is a soliton. This is the ratio of the non-equilibrium to the stationary one. And because the function of t of x is a single function of the initial at 0 time, but with some moving, changed arguments. So this is, you don't have here a factor. So you don't have an amplitude. Only the x variable will be a time-dependent x index t variable, which means that the same deviation you had in the beginning from the stationary goes out on the chain. But then, of course, you are right. If we have some exponential decay of that. So this is not a classical soliton, it's an exponentially suppressed soliton. I called it soliton because you can construct it from the initial ratio and then it just goes out to higher x. Oh, where it is, to higher x. That was the reason I called it soliton. You are right, it's mathematically, classically, it also can reduce its amplitude.
Okay, thank you very much. So we are still open for questions. Anybody wants to? Well, I have more questions. Okay, let me come.
I have one question.
Yes, please.
Yeah, I am Kuheli, and I have one question that when the rates are constant, then the distribution is Gibbs-Boltzmann kind of distribution, right? So when the rates are constant, that means the system is in equilibrium, right? Because when the system is in equilibrium, then only we get the probability distribution, some Gibbs-Boltzmann kind of distribution.
Well, not exactly. Of course, if you are in equilibrium, you get Gibbs-Boltzmann, but you can get exponential distribution also as a stationary one. So there is no detailed balance in behind. It is just a stationary solution, right?
Yeah, and another thing here, you are defining some entropy kind of thing, but entropy, we can define entropy only when the system is in equilibrium, right? But here,
I don't think so. You can calculate your entropy formulas even during the evolution of your system. You can do that. And then usually you expect it grows. No? So we don't call it entropy. The reason we call it gentropy, because we cannot prove that it always grows. So these economical systems, income distributions are not closed systems. They are very much open to their
Yeah.
environment. So it's
Okay,
not,
thanks.
that's not true, it grows, but it has the positivity, the convexity, and all this nice coincidence in formulas. So we don't call it entropy, that's the reason we call it gentropy. But
Okay.
they behave somehow, how to say, in harmony with each other. So it looks in concrete examples that the Gini index higher, entropy is higher. I mean the classical entropy you calculate with Boltzmann formula.
Thank you.
Yes, you are welcome.
So are we having more questions?
Yes.
Yes, somebody?
Okay. I am Ferenc Iglói from Budapest.
Mhm.
And my question is that do you have any relation with if you have some time-dependent disorder in your equations, so that these rates somehow depends weakly or strongly on time?
If the rates are time dependent, I cannot provide a stationary solution. So we did not go into this direction yet, but since we shall meet in Budapest, we can discuss on that later.
Okay.
Yes, more questions?
If you want, I can try to show you another screen if I succeed, a little animation about this LGGR model, if you want.
Yes, please.
Okay, so then I have to push
Experiment.
escape from this, probably.
Yeah.
Yep.
Mhm.
Screen sharing has stopped as the window is closed. How can I make again first the thing? Let me try to, no. Share screen. I cannot yet. Wait, now I make another.
So while we are waiting, is there anybody having another question? Well,
no, it's I have it on my screen. I cannot really show you. I'm sorry. This is.
Tamás, share the whole screen then. If you have it on your screen, just share the whole screen and then we should.
Yeah, but these windows are covering each other. Share screen. A desktop. That's what I have to share.
yeah.
Do you see that?
Yes.
It's okay.
So there is this program Sisyphus, a very small program in X library. So on the staircase, you make the step up, that's the Gros, the rate mu, which is linear in this case. And then you see in sometimes if you are already at a higher position, then it runs away. Then there are these linear preference runs aways. And very often it is just at the low values. And then here you see some statistics, which is of course does not change now anymore. At the beginning, everything was just at the downmost level, but then it developed this tail, and this is a quite long tail. So that's what I just planned to show you.
Okay.
So any other questions?
I just had a personal question because it's interesting me. The Gini index that you defined, that is the official definition of the Gini index. I never encountered it before. I just
Yeah, in the Wikipedia you can check it. So the first equation 8 or something, then you have this double integral and you divide it with the expectation value twice. This is the continuous version. Of course, there is also a discrete version, and there are at least 3 equivalent formulas for that you can prove by some partial integration and renaming your variables. This is a fun to dig into it. Yes.
Very, very well. I will calculate it for my problems.
I hope you recorded the slides, or shall I send the slides to somewhere?
No, it's fine. It's for me, it is fine. Okay. Is there any further question? If not, let's think. Well, I'm not sure how we do that online, but let's thank everybody for this very nice presentation by Biró.
Thanks.
And I think the next speaker can start to prepare his presentation. Will be Stas Burov from Bar-Ilan University in Israel about packets of diffusing particles and universal exponential tails. But I think he's talking from a different desktop, so maybe we'll see a different name there on the desktop.
Okay. Hi, everybody.
Yeah. Hello?
Yep. Can you hear me?
Yes, we can.
Okay. Sure.
I can.
All right. Like this. All right. Can I start?
Yes, please start.
Yes, sure. All right. So my name is Stas Burov. I'm from physics department, Bar-Ilan University. I'm going to talk about universality of exponential tails for diffusing particles. This work was funded by the Pasi Foundation, and I would like to thank the organizers for providing me this opportunity to present my research. All right, so our starting point is Brownian motion, and on this slide, what we can see are the excerpts of the original experiments from Jean Perrin more than 100 years ago, where he tracked small particles of pollen inside water. Okay, so what we see over here, are those trajectories. Okay, and over here it's some sort of an histogram of the different positions of the particles after time t. Okay, see, he clamped all different results from all those different trajectories, and he calculated the distribution, and it followed the Gaussian behavior, of course. For us, of course, but 100 years ago, it was a new thing, and based on the theory or investigations of Albert Einstein about Brownian motion, the stochastic motion of particles, and the simple idea is that a particle inside water fills the different bombardments of all the particles around it, okay, and they contribute in such a way that the behavior becomes a Gaussian behavior. This is what we call today Brownian motion. Now, the question, why Gaussian behavior, and it's so widespread, the fact is that we can is not too broad. What I mean by too broad, so if f of x is distribution of the different small x's, as long as this parameter mu over here is larger than 2, we'll get a Gaussian behavior. Okay? Now, this is why we always, not always, but in a lot of cases, for moving particles, transporting particles, we observe this Gaussian behavior at the center. There are, of course, other central limit theorems, not central, but stable laws. They are named Levy's stable laws, and they are applicable for when this parameter mu is between 0 and 2. But again, the most widespread behavior is, of course, the Brownian behavior, Gaussian behavior for the center. Now, but actually, in the last 10 years or so, there are a huge number of experiments where this Gaussian behavior is actually not observed. Okay, so this example, this from the group of Steve Dranick, they published in 2009. This work, they coined the name anomalous yet Brownian. So they have two examples. One is a colloid, inside an actin suspension. So they do see that the mean square displacement, so how far the particle is actually reached by time t, is growing linearly with time. Okay, but the positional distribution does not attain this Gaussian behavior, but it actually have an exponential tail. Okay, so we can see this exponential tail over here. We also see those exponential tails, straight lines, because of the logarithm over here. We see this exponential instead of Gaussian behavior. Additional system that they observed is again those colloidal beads, but now the suspension was not of actin, but phosphoid bilayer tubes. And again, the same behavior.
Sorry, can I ask a question?
Yes.
If the displacement is linear, shouldn't it be then ballistic transport?
No, so it's x squared. If it was t squared, it was a ballistic, but it's x squared proportional to t.
Ah, x squared. Oh, sorry.
Yeah. So average x is of course 0 because on average the particle is not moving.
Okay.
Okay.
Sorry.
Okay, so now again, we see here those exponential tails. You see, instead of seeing something that is Gaussian, you see a clear exponential decay at different time scales. Yet another example, this time from the work of Chituri, Berthier, and Cobb. So they assembled 4 different systems near glass or jamming transition. Okay. And they analyzed the probability, the positional distribution. And what they see is that, again, instead of Gaussian behavior for those 4 systems, they have exponential tails. Okay, you see here in Lennon-George suspension, this is a numerical simulation, silica, colloids, grains, they all follow those exponential tails. At least for colloids, what do we know? That those tails are modeled, not modeled, but are affected by what is named cage breaking events. So think about a colloid. It's a particle. It's surrounded by many other particles around it. Okay, and the particle is just wiggles around in this some sort of a cage of its neighbors. This behavior over here. From time to time, it will be able to break the cage, okay, and enter in another cage. Those are termed cage breaking events, and they contribute to the large displacements. And this is why those exponential tails depend on this behavior. All right, so actually those are only 2 examples, but there are extremely many examples in the literature, especially in the last 15 years, that people observe this non-Gaussian behavior. And here I just list some of them: active gels, plasma, turbulence, nucleus, etc., 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 cellular nucleus. And then a question arises. Okay, so should we expect this exponential behavior? Gaussian behavior is expected because of the universality and the effect of the central limit theorem. What about the tails? Okay, because central limit theorem does not tell us anything what will happen to the tails. The central part is what happens at the center of the distribution. Okay. So if you use the same approach that Einstein originally, or of the random walk for the tails, so basically we say our position x depends on the n different number of jumps that the particle have performed. And instead of concentrating what happens at the center of the distribution, we will ask ourselves what happens at the tails of the distribution. Okay. Now, each of those small x's, small jumps, is distributed according to this f of x over here. Okay. And we use the large deviation approach and the Kramer's theorem in order to show that actually those tails are not universal, but they are very specific. So we use a specific distribution with a specific beat over here, and we obtain a very specific non-exponential tail. Okay, so this is some kind of a dilemma. We start with a specific system and we'll get specific behavior, and we'll get a specific behavior for the tails. Okay, on the other hand, for the center of this probability density function of the position, if we start with a specific behavior, we will always get a Gaussian distribution in the center. So we have a widespread Gaussian behavior, many systems show Gaussian behavior, And the exponential tails should be very specific to a system. The problem is that we have this extremely long list of different systems that show this exponential behavior without any connection between any connection between these systems. And we can ask our system, is this a coincidence? Probably not. Or there is something that we're missing about the tails. Okay? So we're going back to the blackboard. And we're saying, okay, so we have this random walker. We have n excursions over here. But what actually happens in an experiment? In experiment, we do not count a very specific number of jumps. The experimentalist sets a fixed time, 3 minutes of experiment, 1 minute of experiment. It does not care about how many events have occurred. It just measures for a given time. So if we look on the number of bombardments that a particle fills, the number is random. Okay, so we cannot simply count a very specific number of events that occurred. Okay, we have to assume that the number of events is also a random number. So we use a framework of something what is called a continuous time random walk in order to model this stochastic behavior of the number of events. Okay, so what is a continuous time random walk? A random walker performs a jump from one side to another at unit time. So his clock is 1 second, I jump. The second I jump again. This is the regular random walk. The continuous time random walk is I perform a jump, I wait for a random time, and then I perform a jump again. I wait for a random time, and then I perform a jump again. Okay, so in this scenario, the number of events for a given time is going to be random and dependent on the distribution of the waiting times. Okay. So mathematically speaking, we have the sum of random variables, but the number of variables is also a random number. Okay. So basically, we have to condition on what? On the number of events or number of jumps or number of bombardments that occurred due time t. So here, Pn of x is the probability to be at x after n events, and Qt of n is the probability to perform n jumps at time t. This Qt of n depends on the distribution of the waiting times, psi of tau. Now, if we look closely on this expression over here, and remember that we are interested in the tail behavior, so basically large x's, we see that this form that we obtained from the Kramer's theory for Pn of x for the tails of the distribution for a given number of jumps looks like this shape on the right-hand side. It suppresses small n's, so this Pn of x is extremely small for small n's. It starts to grow for large enough n's. So in order to compute this sum, we can neglect the small n behavior of Qt of n and focus on how this Qt of n behaves for large enough n's. Right? Now, this is what we have done. And interestingly enough, this Qt of n, the probability to perform n jumps during time t, attains this form for large n's. And the only thing that matters is that psi of tau, okay, the waiting time distribution, will be analytical around the tau in the tau goes to zero limit. So expressed as a Taylor series over here. Now, on the left-hand side, we have this comparison, extremely good comparison between the theory and the numerical simulations for 3 different waiting times, and it works extremely well. Basically, we have developed a large deviation form for this probability of Qt of n. Okay, so if we go back and we want to compute the probability density function of finding the particle at position x at time t, we have to perform something in the language of stochastic processes termed subordination. Okay, we have subordination of Pn of x and Qt of n. Now we are interested in large x's, so we need the large deviation form of Pn of x. We already got it, okay? And we need a large deviation form of Qt of n. We also got it, okay? Now what actually happens that all this sum, okay, is the main contribution comes for one single n, this n star, which is proportional to x, up to some logarithmic corrections. This W0 over here is the Lambert W function. Right? So looks a little bit complicated. Okay? This is the result. The result shows indeed exponential tails. Okay, general exponential tails. Why? Because if you look on this function, okay, we see that it depends. It depends on x in a linear fashion up to some logarithmic corrections that appear due to this Lambert function that I mentioned before. Okay, but this, in some sense, the large deviation form for large x's. Right? So what we basically found, okay, that there is universality for the tails that is similar to the universality of the center. In what sense? So if we look on px of t, the probability distribution function, we can describe this in this form that is the form of large deviations. So the regular form of large deviation is when the time is large and x is small, this large deviation function I is quadratic. Okay, and this is why you observe this Gaussian behavior at the center. This is the center limit theorem, okay, in some sense. On the other hand, what we have shown is when x is large and we absolutely don't care about what the time is can be small, okay, as opposed to the Gaussian limit, we see that this large deviation function is basically linear. Okay, instead of quadratic, it becomes linear. So this exponential behavior that observed in many systems is an outcome of what we suggest is an outcome of a universality of the behavior of random sums. Okay. When one should expect to observe this exponential instead of Gaussian behavior? So in any case of situation that is similar to what I showed you before, the number, it's basically a rare event behavior. So here's a trajectory of a particle. Okay. From time to time, most of the time, the particle is doing some Brownian motion, but from time to time, we will expect to see some large jumps. Now, those jumps, okay, they are rare, but their statistics start to appear already for small times. For example, this is another case with exponential tails, is the particle that is moving a little bit on a surface, jumps into the bulk, and then returns. Okay. Our claim is that for times that are not too long, what one would observe is the exponential tails instead of the Gaussian tails, because this behavior, universal behavior that we state over here, does not depend on the time. And for short enough times, okay, we won't see this left-hand side, and the only thing that will be left is the right-hand side and exponential tails. To summarize, okay, in 2 sentences, what we claim here is that this widespread exponential behavior of the tails that have been observed in extremely many cases in the last 15 years is on the same footing as the Gaussian behavior of Brownian motion. The tails are universal due to some mathematical behavior of random sums with random number of ingredients. Okay, I also would like to thank my collaborators on this work, especially Eli Barkai from my department and Wan Li Wang, also from Bar-Ilan University. Thank you. You're muted.
You're muted, Claudius. You are muted. Still muted.
Okay,
Now,
sorry. Thank you very much. And we have time for a few questions. Maybe it's all done. You want to start?
yes, thank you very much. First of all, thank you very much for this very interesting presentation. We have played a lot nowadays.
Zoltan, you are muted, probably.
I'm not muted, so is it okay?
Zoltan?
Yes, yes.
I think
Yes.
everybody else hears me. So,
I can.
okay, but I think the others can hear me, no?
Yes, we can.
Yeah.
Yeah. So thank you very much for this presentation. Lately, we have done some experiments when we have put some nanospheres between two sheets, between two plates. And we observed exactly what you have described here, because what happened, and this is what we have observed, that the nanospheres, which are making a Brownian motion inside the liquid, they sometimes stick to the surface. And sticking to the surface, they have a kind of one type of diffusion on the surface. Mm-hmm. And from time to time, they unstick from the surface and they then have a bulk diffusion. And this is exactly what you have described here. So we were also puzzled about what we see about the tail, but what you have offered here, thank you, it's a very nice explanation, which explains what we have observed.
Yeah, we're now conducting also a very specific model when we have, for example, it's a little different from what I described, but it's on the same line. So if you have two-state model for the diffusion, like you do, for example, I have a diffusion 0 when you stick to your surface, and D1 when you're just performing in the bulk. You will see those exponential tails for sure.
And we did it. So we did it. So
well, you know, I'm a theorist. If you're performing the experiment, it's more than a verification, of course.
Okay. The student who have done this is also present here, so he's very happy to hear.
I would like to contact you, or if you would contact me.
Okay, thank you very much.
Yeah, sure.
Yeah, I also would have a very short question. I mean, we all know the center limit theorem and that you get a Gaussian. I was not aware personally that the Gaussian is valid only for the center, not for the tail.
Yes.
Can you give a short reasoning for that? Why the Gaussian is not valid for the tail?
So why the Gaussian is only for the center? Well, let's see.
Simple hand waving argument.
So the simple hand waving argument, the Gaussian central limit theorem. It's why it's only on this for the center. When you exploit this, okay. So first of all, okay, the mathematical outcome for this. I'm sorry, where is my pen? So this large deviation function. Mm-hmm. Basically, when you perform this calculation, right, the quadratic form appears only in a very specific limit of this axis over here. Mm-hmm. Okay. Why exactly it's quadratic? I don't really have a hand waving argument. Okay. But it's a very specific limit that when you perform this calculation, you can see that the only thing that matters, okay, is the second moment. Mm-hmm. Okay? And the second moment, when you expand this, the expanded moment is proportional to d squared, and this is why you have a quadratic form.
Okay, I understand.
Other than this mathematical claim, not really. Okay, I
understand. The center limit theorem corresponds to a moment expansion. Okay.
Yeah, basically, that's it.
Yeah. Okay, we come to a conclusion. Thank you very much for this really interesting talk. I learned a lot. And well,
thank you.
And we come to the next speaker. I think he's using the same desktop you were using. David Kessler, also for Bar-Ilan University of Israel, on regularized Boltzmann-Gibbs statistics for deep non-confining potentials. Yes, please, David, go ahead.
All right. So first of all, I want to thank the organizers for giving me the chance to talk, and I'm very sorry that couldn't be there. I always heard that Cluj is a very pretty city, and I was looking forward to visiting, but some other time, I guess. All right, so I'm also talking about Brownian motion, but a different context. Brownian motion, when the motion is in a deep potential, but the potential is not deep everywhere, so that it doesn't go off like a regular harmonic oscillator, it doesn't go off to infinity, but in fact, at large distances, the potential is flat. So the particles at long distance, if they manage to get out far enough, in fact, they're free to wander around diffusively. And then the question is, so the particles can basically escape the well, go off the large distances where they're essentially free. And then the question is, what happens, as we'll see, to Boltzmann-Gibbs statistics that is our standard tool for handling equilibrium problems. So we have, and this is not exactly an equilibrium problem, and the question is to quantify, but nevertheless, it looks a lot like an equilibrium problem, and we want to actually quantify all that. So this is work that was done in collaboration with Eli Barkai from our department, Celia Antoniodo, who's from Rio de Janeiro, and her student, postdoc Luciano De Faveri, and it is an outgrowth of work that was done by a former student of Eli's and mine, Erez Aguillon, who's currently in Dresden at the Max Planck Institute. So the current work is actually on archive, and the previous works with Erez Aguillon are a PRL and just appeared the long version in Chaos, that solitons and fractals this year. All right, so let's start at the beginning with simple stuff that everybody knows. This is the standard case when you have Brownian motion in a confining potential. So we have a Brownian motion particle who's diffusing in a confining potential V, and so V goes off to infinity as X goes to plus and minus infinity. So the particle is always in the well. And so the standard treatment, one standard treatment is the Langevin equation, but the other way is to describe it by a Fokker-Planck equation, which is given here. We have that dp dt is the diffusion plus the drift term because of the presence of the potential. All right, and so if you're interested in long time behaviors, as t goes to infinity, then the system goes to a time independent state, which is the equilibrium state. So you set dp dt equals 0 when you solve the simple differential equation, the ordinary differential equation for p of x, and what you get is you get the Boltzmann-Gibbs distribution, the Gibbs distribution e to the minus v over kt that we know and love. And of course, it has to be a normalized distribution, so you have to divide it by the partition function z, where z is just the integral of e to the minus v over kt over all x. And then that is as long as you're, as far as long time properties, equilibrium properties, everything is given once you know equilibrium. Then if you want to know what the mean value of x is, the mean squared value of x, whatever the mean value of the potential, whatever you want to know, is done by integrating O of x against the equilibrium distribution. This is what we mean by Boltzmann-Gibbs statistics in the overdamped case. All right, so next in the line of complicating the story is what happens when you have a non-confining potential. When v of x, instead of going to infinity, when x goes to plus minus infinity, it actually goes to 0 or to a constant. It would do the same thing. And now life is a little more tricky because e to the minus v over kt is still a time-independent solution of the Fokker-Planck equation. If you plug it into the Fokker-Planck equation, it satisfies that the derivative, the right-hand side of the Fokker-Planck equation is 0. So therefore, you would think that dp dt is 0, and this is the time-independent solution. So it should be the solution for large times, but in fact, it's not. How do you know it's not? It's because when you try to calculate the partition function z, since e to the minus v over kt, in fact, goes to a constant when x goes to plus and minus infinity, therefore the integral diverges and z is infinite. And we have a solution of the Fokker-Planck equation, but it's not a legitimate solution. It's not a normalizable solution. So it can't, we have to do better than that. So what happened? It's not that hard to figure out. What happened is that long times, the probability the particles can escape the well and they start spreading out over all space. And now at any finite value of time, however, in fact, even the particles that have escaped the well, all they're doing is diffusing. So there's a limit to how far they can spread. They spread the standard diffusion length, which is the square root of 2 dt. So at any given finite time, the particles are all contained within if you started out with a localized initial distribution, the particles are all contained within a distance square root of 2 dt from the origin, even if they're outside the well, which has a width of order 1. But you see the width is constantly spreading because that's what happens with diffusion. The packet, obviously, the Gaussian packet of the diffusing packet is constantly spreading in time, like the square root of t. So therefore, P of x is always time dependent. There's no limit where P of x and t is just a function of x. It's always intrinsically time dependent. You can't just say, you can't start out saying dp dt is 0. And in fact, you can solve the problem at long times. And it's a time-dependent thing. When you do that, what you find is, in fact, to leading order, the probability distribution as a function of x and time factors into 2 different factors. The first factor is the e to the minus v over kt, which describes the confinement of the particle in the well. But for the particles that are outside the well, where v is 0, and this factor is 1, well, then things are controlled by, in fact, just the standard diffusion kernel, e to the minus x squared over 4 dt divided by 1 over the square root of pi dt. So in the inner region, where v is not small, then, in fact, if x is much, much smaller, if we're talking x is of order 1 and t is large, the Gaussian factor, e to the minus x squared over 4 dt, is in fact exponentially suppressed. It's Gaussianly suppressed. And so, it's x is small, so therefore that's 1. And therefore the P of x and t reduces to e to the minus v over kt divided by the square root of t, divided by the square root of pi dt. So therefore, it's in fact as if there was a Gibbs distribution, e to the minus v over kt, but the partition function is in fact time dependent, increasing like the square root of t. So in fact, when t goes to infinity, the partition function does diverge, but for any finite time, the partition function is perfectly well defined. And in fact, if now you want to calculate any statistical quantities, then what we show is that in fact, you just can use this time dependent P of x and t, and what you get is you get Boltzmann-Gibbs statistics in the inner region with a time-dependent normalization. So as long as the quantity you're measuring is only sensitive to what's happening in the inner region, then the problem is in fact just given by Boltzmann-Gibbs statistics with a time-dependent normalization, which measures how many particles basically are left in the well. And as time goes on, there are fewer and fewer and fewer particles left in the well. So therefore, but if the observable doesn't see the particles outside the well, say you're measuring, for example, the mean potential energy, so the mean potential energy at long distances is 0, essentially. So therefore, you're measuring you're getting the right answer. If you have an observable, say the mean squared displacement, however, which is sensitive to the particles outside the well, of course, then that's very sensitive to the Gaussian e to the minus x squared over 4 dt part of the game. And so you have to work a little harder to get that, but you can do everything you need to do, knowing that what in fact you have is a time-dependent distribution. So that's what happens generically when we have non-confining potentials. And if you think that non-confining potentials is a very strange, obscure problem of interest only to people who have nothing better to do with their time, in fact, you should just think of a particle in the atmosphere, right? A particle, right? If in fact the atmosphere was truly isothermal, which it's not, but if it had been isothermal, in fact, although then the atmosphere at long times would escape. And right, and we ignore that because of the temperature dependence and things like that. The atmosphere gets colder as you go higher and so forth and so on. There are all kinds of complications. But if you had an isothermal atmosphere, in fact, you wouldn't have an atmosphere if you waited long enough. So, and this is then would become very relevant. All right. So now we want to turn to what happens when the potential is still non-confining, so the potential goes to 0 at long distances, but now instead of being order 1 in the inner region, is deep. So it's very strongly confining in the inner region, but not confining at all when x goes to infinity. For example, you could imagine a potential like this, u naught over 1 plus x over x naught squared, so it goes off like 1 over x to the 4th with long distances, goes to 0 long distances, but if u naught is much, much greater than 1, then in fact the potential energy of a particle in the well is very big and negative, so it's very strongly bound inside the well. All right, and so therefore what happens is now, in order to get to large X, it takes an exponentially long time because it has to climb out of the well, and the well is very deep. So it's, in fact, it takes a long, long time to get there, times of order e to the u naught, for the particle to leave the inner region and then start diffusing around. And until you wait that long, if you start with a particle that's in the well, the particle, in fact, thinks for times up to order e to the u naught, that it's in a standard equilibrium situation with Boltzmann-Gibbs statistics. But then we're back to where we started from. If now z looks like it's in fact should be, if we're standard equilibrium, z should be the constant. It should be the integral of e to the minus v over kt. But it can't be, because if you would integrate e to the minus v over kt, z is still infinite, because at large distances, e to the minus v over kt goes to 1, the integral diverges. So is there any sense in which there's an effective constant z effective that's so that you can do standard Boltzmann-Gibbs statistics for times, for these intermediate times now, which can be very, very long times, but shorter than the time it takes for the particle to actually leave the well. So again, what we have to do is solve the time-dependent Fokker-Planck equation, and at long, but not very long, not super long times, and large and not too large x's, again, the solution is e to the minus v over kt with some normalization c. And at long distances, p satisfies the diffusion equation. And now it's this story is slightly different because it's the same diffusion equation, but what you have to match to is not something that's decreasing like 1 over the square root of t. In fact, in the inner region, p should go like the c should be a constant, because in the inner region the particle thinks it's in equilibrium. And so, in fact, the relevant solution at large distances is a different solution of the diffusion equation, not the standard solution. It's an ERF-C, which also goes to 0 like a Gaussian at large distances, but goes to a constant for small distances. And then you can work out what C is, because at any finite time, everything has to be normalized. And so you can break up the integral into the inner region and the outer region. The inner region is the integral of e to the minus v over kt. The outer region is the integral over the ERF-C. If you do a subtraction, take away a 1 from both integrals, then in fact now what you've done is you've gotten a integral which is finite, because you've taken away the 1 and you put it over here. The second integral is in fact of order square root of dt. The first integral is a constant, is a finite number, but it's exponentially large. It's order e to the u naught, because at x equals 0, it is in fact has the value e to the u naught. So you have the normalization has two contributions. One is a constant, one is increasing with time, but the constant for all normal times totally swamps the time-dependent part, and therefore, effectively speaking, the normalization is time-independent. So what you have is you have a regularized partition function, which is finite, and that dominates everything. It dominates the time-dependent part of the partition function until t's are exponentially large. And for these very long, times which are intermediate, but to be quite long on the scale of the normal dynamics, p in fact is again a product of the inner part, which is e to the minus v over kt, times now not a Gaussian, but an ERF-C, and the effective partition function is now this Z naught, which is a constant. And that is what controls the statistics. So for exponentially long times, of course, once the particles, if you do wait exponentially long times, of course, then the particle does escape and Z becomes time dependent, just like, and you revert to the non-D case, because for those long times, in fact, you're allowed to escape the well. All right, and just to show you one numerical example of how that works in practice, what we've done is, this is just a simulation of the Fokker-Planck equation, starting out with the particle at the origin and measuring the mean square displacement. And so what you see is at very, very short times, of course, the particle equilibrates in the well, and then effectively the mean square displacement goes to a constant. And then at times you see, which are very long, orders of 3 or 4 orders of magnitude longer than the equilibration time, which is order of 10th here, it then starts increasing like the square root of t. And so it's like t, excuse me. And this is done for different values of the temperature. And you see that as the temperature rises, of course, the difference between then the very long time becomes not quite so long, and therefore, and it's eventually at large enough temperatures, you can escape the wells on times which are sort of normal, and then you lose this quasi-equilibrium phase. But for any normal, there's a whole range of temperatures for where you have a long period of time in which the system is essentially in equilibrium, but it's an equilibrium that's doomed to die because the particles eventually will leave. And so that's the message, is that this is a problem where, in fact, again, you have to look at the time dependence, but if you look at the time dependence, then you can make the problem the problem simplifies, and in the end of the day, you can treat the problem as it has this product form of an inner part, which is time independent, and an outer part, which is diffusion controlled. Thank you for your attention.
Okay, thank you very much for this interesting talk. We have time for 1 or 2 questions. Let me start. Your approach was, of course, very naturally from the particles being in the well and then trying to get out and finding the distribution function. Would it be possible to view it also from the other limit? So you have a particle diffusing on the flat potential and sometimes dropping into your well and getting out again?
So in the case of the deep well, that's an interesting thing. I haven't looked at it, but yeah, if you started with the particles in the flat part, they would wander around, and some number of particles clearly, because it's like having a trap at the origin, right? So some percentage of some number of particles would fall into the well, and once they fall in the well, it's going to take them, super large times to get out. And so yes, then in fact, you'd have to calculate how many particles get into the well. It's an interesting question to work that out, but we haven't worked it out.
Yeah. Okay, are there further questions? Well, if not, let's thank everybody, David, and for this interesting talk. And we are in time coming to our next speaker, Artem Ryabov from Czech University in Czechoslovakia, on non-equilibrium transport and phase transitions in driven diffusive systems with space continuum dynamics. So, Artem, are you there?
Yes, hello. Now I will try to share my screen.
I think maybe David has done. Yeah, okay, good.
Okay. Share.
Yeah, seems to work out fine. Good. Please go on.
Thank you very much. Thank you very much for the introduction. Now you can see a title of my talk, which is a bit lengthy, I admit, but the most important keywords in it are non-equilibrium phase transitions and driven diffusive transport. Yesterday, when I was thinking more about the content of this talk, I wanted also to present to you some of our most recent results. And to this long title, I have also added another subtitle, which reads Duration of Transition Events in Crowded Non-Equilibrium Systems. So the talk basically will be from two parts. First one will be about collective properties of classical non-equilibrium driven systems and about phase transitions and about one model that we have studied. And in the second part, we will focus more on the kinetics of individual particles, more on a packed particle problem, and formulate a kind of a Kramer's problem in interacting environment. The model which I would like to present and the situation is inspired by something what is called single file diffusion. Single file diffusion is a kind of diffusion in confined spaces, and single file in the name refers to the fact that particles diffuse in a confining environment, and the environment is, or the pore is so narrow that they cannot overtake each other because they interact through hardcore or steric interactions. So diffusion of such particles preserves the order, and it has many interesting properties. And in addition to this, it occurs in many situations also in nature, which we know. For example, in the middle of the screen, you can see a typical situation of membrane transport where single file diffusion can take place, or like on the left of the screen, it's our favorite summer activity in Czech Republic, which is waiting in traffic jams because of work construction. It's also kind of a single file transport because we cannot overtake one another. In the bottom left of the screen, there is a transport in zeolites, and then you can see also on the screen nanotubes and some transport of molecular motors. So this is an inspiration for the model which we have studied. And now in the next part, let me introduce the model. The model is called Brownian asymmetric simple exclusion process. To people who know, it reminds exclusion processes for certain reasons. And it's a minimalistic theoretical model for a single file diffusion in periodic environments. So we have in the model, we have n degrees of freedom. Each degree of freedom x corresponds to a position of a particle in one dimension. And each particle evolves according to a Langevin equation, which you now can see. It has three terms. So first one is a drag. The constant drag creates an average flow of particles through the pore. On this schematic picture, which you now can see, the arrows represent the schematic drag in one direction. So particles will be flowing in one direction. The last term is thermal noise. In our case, noise is simply a Wigner process, a Gaussian white noise. So without any interaction, without any potential, each particle will diffuse by a normal Brownian motion. And the middle term, which you can see, represents periodicity of the environment. It's the third important component in the model. We will assume that particles move in some periodic pore. For example, it can be entropic potential, which when it has a minimum, it means that particles is in a wider space, and when it has a maximum, which particle has to overcome, it is in a some more confining space, for instance, or it can represent some binding sites inside the pore where particles diffuse. And of course, the important component of the model is that particles interact as hard spheres. We have a diameter, sigma, of a particle, and then they cannot cross, they cannot occupy a space which is occupied by other particles. Altogether, if we put all this into one picture, then we can imagine that particles basically locally are diffusing in a tilted periodic potential. Plus, they have their own size, so they cannot occupy the same space, and they are just reflecting if they collide. This is the dynamics. The model now now comes the jump. Actually, I have decided to skip too many technical details and instead speak about the results. So we have analyzed this model of single file diffusion by Monte Carlo simulations, by density functional theory, and by linear response theory and their combinations, and found quite interesting and surprising features, and they are summarized now on this next slide. I understand that there is now too much information, so let's read this slide line by line. First, we have base up versus ASAP. Base up is our Brownian asymmetric simple exclusion process, and ASAP is a well-known asymmetric simple exclusion process. The ASAP, it's a lattice model. So this is the first reason why we can compare the two, because basically everyone would guess that motion in a periodic potential, when the thermal energy is not very high compared to the barriers, could or should maybe in some limit resemble hopping on a lattice of particles. And ASAP is exactly the model where we have particles which hop on a lattice. Now it's schematically plotted on the right of the upper of the screen, and each particle can occupy simply one side, which represents exclusion interaction. Similarly, in our model, we have hardcore interaction. So first thing what we expected from our simple model when we started to study it, that we basically will reproduce most important properties of ASAP. And what are the most important properties of ASAP? Well, there are many of them. This is also why it's called Ising model of non-equilibrium statistical physics. But for us, the most interesting was the stationary state and different phases in the stationary state. So stationary state, we should maybe divide into two parts. First, we can have a non-equilibrium stationary state in a system with periodic boundary conditions. It's like you see on the schematic of ASAP. Particles basically are hopping on a lattice, and after some time, the system reaches stationary state where there is a certain current or flow of particles. And the most important characteristics of this stationary state is how current depends on density of particles. This dependence, it has a meaning, like in equilibrium statistical physics, we have the equations of state. If we know this dependence, we can predict state and also phase transitions in this system. So this was the first, what we looked at, was how current of particles for the system depends on density in our ASAP model. And this is plotted now in this graph where there are many, many curves. And let's start with the straight line. For example, here we have a straight line. Here is a current of particles, and density. In our case, density simply is a number of particles per number of wells on a lattice in the system. And linear dependence corresponds to non-interacting particles. If there will be no interaction, then of course increasing density means that we proportionally increase current. The more particles we have, the more they flow. ASAP, this paradigmatic example, it has a current density relation which is parabolic. It is shown by the dashed line, the lowest line here on the graph. It corresponds to ASAP. Basically, for small densities, we have increase of current with increasing the density, but then blocking comes into play, and the current density relation saturates for density 0.5, and then goes down, because the more particle we have, the bigger traffic jams we create, and the more they block each other. So this is what we expected first to see in BASEP, but all other curves here in this figure corresponds to BASEP results for different diameters of particles. And what one can see is that for small particles, these are blue lines, these are lines which grow very fast. So for small particles, we don't even have a maximum in current density relation, but we have kind of a current which is even faster than the current for non-interacting particles in the similar system. And only with increasing particle size measured in terms of a period of potential, we can create a maximum, and for creating the minimum. And only for a limited, actually for particle size is about 0.75 in terms of periodicity of potential, we can see something which resembles ASAP, but in all other regimes, we have a very different dynamics. Okay, this is nice. We have maximum and minimum, but what does it mean? As I've mentioned, this relation is kind of, it's of similar importance as an equation of state, because having extrema in this relation means that in a system with open boundary conditions, this is usually what occurs in nature. For example, in the membrane transport, particles enter system from one side and exit from the other side. And of course, they have some input rate and output rate, which are given by environmental conditions. And the question is how density in the bulk looks like. And we can predict this density by knowing the relation, the current density relation in closed system. And it is well known that in ASAP, we have 3 phases of this non-equilibrium steady states in open system. And in our case, it turns out that this complicated current density relations can lead up to 5 phases, again, dependent on the particle density. So it's much more complex. So here, these results are published in these 2 references, which I've mentioned, and they're related to this long title of this talk. We have a very simple model of many particles which are driven out of equilibrium. They interact and diffuse for periodic potentials. Now we have very complex behavior, and their collective properties lead to 5 non-equilibrium phases and interesting phase transitions. But after saying this, we wanted also to understand what is going on physically. So we decided, okay, let's see why this appears, why this happens, what is actually so complicated in such a simple model. And for that, we focused on dynamics of individual particles. So now we come to the second part of my talk, where for that model, which we now discussed and saw that we have up to 5 non-equilibrium phases and very nice current density relations, let us focus on kinetics of one single particle. Experimentally, this would correspond that we label one particle by some fluorescent probe or something like that, and we will follow its motion in the steady state and periodic system. As particle will be flowing, we will follow single trajectory and analyze. And the basic quantity, what we can measure, and what we speak in the following, are times of transition from a given well to a neighboring one. So the measurement, for example, in simulation runs like this. We follow a particle and we start to measure a time when it crosses a given minimum, for example, the middle one. Now we measure a time until it reaches either the right or left minimum, and at that instant we record either tau plus if it jumps to the right, or tau minus if it jumps to the left. And we make statistics separately of these times, statistics of tau minus and statistics of tau plus. So in terms of probabilistic language, these are conditional first passage times, and they are conditioned on an event that transition happened. We analyze conditional statistics of how long does it take to go, let's say, downhill in this tilted pair potential, and how long does it take to go uphill, and how the interaction can influence these statistics. Of course, the very basic question, which actually turned out to be the most important, is which one of these times is longer on average. Of course, I was expecting that basically we should go faster downhill. It's clear we are going downhill, we are driven by the force. So tau plus should be shorter than tau minus, but it turns out, and this is the second interesting message which I would like to tell you in this story, that the answer is far from being so simple. It turns out that it depends very much on density of particles. But apart from that, there is a universal inequality between these times, which one maybe wouldn't expect. So results of simulations are plotted now on the graph that you can see. And they are plotted as the independence on a diameter of a particle. 0 is a very small particle, and 1 means the particle has a length of a period of one potential. And colors, red curves correspond to high density, and blue curves, there are 2 here, they overlap, they correspond to a very small density of particles. 0.02 means that we have 100 potential minima with periodic boundary conditions and only 2 particles. Basically, this is a non-interacting system. They met a few times during the simulations, during a long simulation time. So now we see that if particles are not interacting, then squares, which corresponds to uphill times, and circles actually overlap. So for non-interacting particles, interestingly, we have the times going uphill and downhill are equal on average. But for interacting particles, now we can see that the times can be both smaller and larger than the ones for non-interacting ones in the system now with high density. The circles are downhill times, and here we can observe inequality that in all this range this downhill time, tau plus, going with the flow, is actually longer than going uphill. So the uphill time is shorter. And for small particles, the difference, the absolute value of the difference is not that huge. But for example, for larger particles, we have 1 order of magnitude. So it's not an epsilon effect, which could be attributed to an error in our simulations. It seems to be a real effect that going downhill in an interacting system, in an interacting single file system, takes much longer time than going back uphill. So regarding the non-interacting, regarding the zero density limit, of course, we have searched for the literature, and in the left column, we were disappointed and very jealous that someone discovered this already. There are many nice references. The oldest now one that I know is this 2001 fluctuation noise letters, where for non-interacting, for a single Brownian particle, it was proven that the times are identically distributed, and this nice result is rediscovered. It seems that it's rediscovered, like we rediscovered this result, so many people do, and one of the latest, it's generalizations to many dimensions. It can be found here. As for interacting particles, it seems that apparently, I don't know, I haven't found any other references studying this. If the audience would know any papers for this transition times, I would appreciate if you can mention them to me. I know only regarding this system, it's our work from which we published last year, and this year a very nice letter appeared from Tolia Kolomaisky, and inspired by our work. This is not the reason why it's nice, but it's nice because they created a simple lattice model which is exactly solvable, and they managed to calculate even analytically inequality between downhill and uphill times. It's a very fresh result.
Artem, you have to slowly come to an end.
Exactly. And I have, in the last minute, actually, I'm coming to the conclusion. So, of course, basically, if to summarize this, we have found that interaction implies breaking of symmetry of times, which is not present in the single particle system. Uphill transitions are faster, which was surprising for me first. And the symmetry breaking appears to hold universally in interacting system. So what, of course, the last thing which I would like to mention here is the most recent work. We started to think, okay, we have really simple model, and if one has simple model and discovers something for that, it can be universal. So we can go from transition times to something more complicated and study, for example, times in Gambler's ruin problem, which basically corresponds or can be mapped onto cyclic processes. So we can go from times from individual transitions to times that describe how long does it take for some cyclic stochastic process to complete a cycle. And such cycles appear, for example, in modeling of molecular models. And this is just an advertisement of our recent study where we focused exactly on these times and tried to understand how interaction, and now not among the particles as in single file system, but with the environment, can influence these times. And I'm not going to go into details, it's just to mention as a conclusion that it seems that measuring cycle or transition times can give us valuable information about interaction among particles in the system, about how much they are important. And also it seems that it can bring a new information about what processes which are going on in the environment. In this last study of us, we have kind of observed that conditions, for example, how far environment is from equilibrium, also influences symmetry of the times. And this is all. Thank you very much for your attention.
Thank you also very much. We don't have much time for a question. Let me then ask just a single obvious question, probably many people have in mind. If the uphill times are much faster than the downhill times, intuitively, it seems that you cannot have a finite current downhill. So what is wrong with this intuition?
Yes, it's yeah, I apologize. I perhaps skipped one important step in this explanation. It's because the times are conditioned on the fact that event happened. Of course, there are many events where particles jump downhill, but only a few when they go uphill. So this proportion, or let's we can say that it's inequality of splitting probabilities, that it's much more probable to go downhill. So despite that it takes longer, there are much more particles who go downhill than the uphill.
Okay, thank you very much. Let's thank Artem.
Thank you.
And we are coming to our last speaker of this morning session, Yuichi Itto from University of Stuttgart. Analogy of fluctuating diffusivity of NR-proteins particles to thermodynamics. So, yes, you're already ready?
Yes.
Please go.
Screen is okay?
Yeah, it's
Perfect. It's perfect.
And the sound is also okay?
Yes.
Yes, it is.
Okay. Hello, everyone. First of all, I would like to thank the organizers for organizing this wonderful conference. And I also would like to thank for giving me this wonderful opportunity. In this talk, we discuss a formal analogy of fluctuating diffusivity of RNA-protein particles to thermodynamics. I would like to emphasize that our discussion is not about thermodynamics of diffusive systems. This is outline. Firstly, we discuss fluctuations of the diffusion coefficient of RNA protein particles found in an experiment. And motivated by this experiment, a recent work has introduced the entropy associated with diffusivity fluctuations and has found that there exists an analogy with thermodynamic relation concerning temperature for the entropy. Therefore, secondly, regarding the average value of the diffusivity as the analog of internal energy, we identify analogs of the quantity of heat and work. And thirdly, we establish the analogs of the second law of thermodynamics described by the Claudius inequality. A recent experimental work has revealed that messenger RNA exhibits an exotic diffusion phenomenon in cytoplasm of a living cell. And here, messenger RNA is labeled with fluorescent protein, and the cytoplasm is an area outside of the cell nucleus. The experimental result shows that the diffusion coefficient fluctuates depending on the local area of the cytoplasm. Two different cell types were studied. One is Escherichia coli cell. This is bacterium. And the other is Saccharomyces cerevisiae. This is yeast cell. This is example of trajectories in the case of Saccharomyces cerevisiae. To characterize the diffusion property, the mean square displacement has been analyzed at the level of individual trajectories. The mean square displacement scales for elapsed time t like this form. And the diffusion exponent alpha appearing here is approximately constant, and the value is less than unity. So this is the traditional anomalous diffusion widely discussed in the literature. In contrast to the diffusion exponent, the diffusion coefficient fluctuates in a wide range. This is the experimental data, and this is the semi-log plot of probability distribution of diffusion coefficient. The triangle and the cross symbols are data for E. coli with different elapsed time, and the circle symbol is the data for S. cerevisiae. And as you can see, the data is nicely fitted by the straight line. And this is semi-log plot, and therefore the diffusivity obeys the exponential law like this form. And here D0 is the average of the diffusivity, and this quantity becomes a central quantity in our later discussion. The exponential fluctuations comes from heterogeneity of the cytoplasm. The importance of the exponential diffusivity can be also found for other biological systems mentioned here. The experimental work has also pointed out that the exponential diffusivity fluctuations is a maximal entropy distribution. Accordingly, a natural question arises. If exponential diffusivity fluctuations can be derived from the maximum entropy principle. Indeed, the answer is yes. The point is that the time scale of variation of diffusivity fluctuations is much larger than that of dynamics of RNA-protein particles. Therefore, the state of the cytoplasm with exponential fluctuations may maximize a certain statistical measure, and this is the measure about uncertainty of diffusivity fluctuations. We will discuss this entropy later. Now, this entropic approach has also found an interesting result. Let us consider D0 varies slowly, the timescale of which much larger than dynamical one. In such a thermodynamic-like situation, this relation holds for the entropy associated with diffusivity fluctuations, this S tilde. And as you can see, this relation has a formal analogy with thermodynamic relation concerning temperature. If S tilde is identified thermodynamic entropy and D0 is identified as the analog of internal energy. Therefore, we discuss a formal analogy of fluctuating diffusivity to thermodynamics. We identify the analogs of quantity of heat and work, and also we identify the analog of the Claudius inequality. The present discussion may contribute a deeper understanding of the fluctuating diffusivity in view of the laws of thermodynamics. Let us regard the cytoplasm as a medium for the diffusion of RNA-protein particles, and then we imaginarily divide the medium into many small blocks, like this. In each local block, the diffusivity is slowly fluctuating because the the time scale of variation of diffusivity fluctuations is much larger than that of dynamics of RNA-protein particles. For this situation, we identify the analog of the internal energy as the average value of the diffusivity. And we are interested in a thermodynamic-like situation. Therefore, we consider a process connecting two different states. And in these states, diffusivity fluctuations are infinitesimally distinct from each other. And we consider the small change of UD along this process, which is given by this equation. And here, delta P is change of the statistical form of fluctuation, and delta Di is the change of the diffusivity. These changes may be realized by the change of temperature and the change of external parameters. Here, we make a comment on the change of diffusivity. We assume the Einstein relation holds for the diffusivity. So diffusivity is proportional to temperature, and the proportional coefficient is denoted by C. And we consider the change of the quantity C may be realized by the expansion or compression of the cell. In fact, recent experimental work has reported this feature in this reference. Therefore, we have the analog of the first law of thermodynamics with the following identification. We are considering the diffusivity is the analog of the internal energy, and it is natural to identify the analog of work in this quantity, and therefore the analog of the quantity of heat is identified as this quantity. Let us examine these analogs for the exponential diffusivity fluctuations. To do so, it may be useful to write the distribution as this form. And here, beta is defined by this quantity. And it is understood that the change of beta corresponds to the change of temperature T, because B times Di is independent of the quantity C. And these analogs, I mean the quantity of heat and work, are calculated to be these equations. And it may be of interest to see the analog of the quantity of heat is described by the variance of the diffusivity. Next, we establish the analog of the second law of thermodynamics. For it, we introduce the entropy associated with diffusivity fluctuations. Let us consider a lot of replicas of the medium like this. And each replica is different from each other in terms of the local diffusivity fluctuations. The point is that each local block is independent from others because the diffusivity is obtained from individual trajectory. And in this case, the total number of replicas can be calculated by omega explicitly. So we introduce the entropy associated with diffusivity fluctuations as this quantity. And this quantity turns out to have the form of Shannon entropy. Using this entropy, we can also calculate the change of entropy, which is given by this form. And in the case when P is equal to the exponential fluctuations, we have these relations. S tilde is defined by this quantity. And it is noted that in this relation, the quantity C is fixed inconsistent with the thermodynamic relation concerning temperature, because this partial derivative indicates that the volume of the local block is kept unchanged. To obtain the inequality, we quantify the difference between some fluctuation distribution P and the exponential fluctuation P0 by employing Kullback-Leibler relative entropy. And this relative entropy is positive semi-definite and vanishes if and only if P is equal to exponential fluctuations. And then we characterize the change of the distribution P in this form. And here, yes.
Slowly, you have to come to an end.
Okay.
Yeah.
And the P, I have 5 minutes later. I have. Do I have 2 minutes?
Hmm?
Do I have 2 minutes?
Yes.
Left? Okay.
No, not left.
And yes, P star is satisfying this relation. So P star is more close to P0, I mean exponential fluctuations, compared to the sum fluctuation distribution P, and the constant gamma is in this range. An important feature of the Kullback-Leibler entropy is convexity, which is described by in this form. And since P is changed to, since we are considering the change of the fluctuation distribution P, of course, the Kullback-Leibler entropy also changes. Therefore, we examine the change of Kullback-Leibler entropy, and this change is described by in this form. And the important point is that the convexity offers this inequality. And the gamma is positive, and the quantity within this bracket is negative. Therefore, the change of the Kullback-Leibler entropy is not positive. On the other hand, the Kullback-Leibler entropy, the change of Kullback-Leibler entropy is calculated to be this. Therefore, we obtain the analog of the Claudius inequality. And of course, this constitutes the analog of the second law of thermodynamics.
I think you have to come to a conclusion here.
Yes. We have discussed an experiment that RNA-protein particles exhibits exponential diffusivity fluctuations. And based on this experimental result, we have regarded the average of diffusivity as internal energy, the analog of the internal energy. And we have identified the analogs of the quantity of heat and work. And we have also established the analog of the second law of thermodynamics in the form of the Claudius-like inequality. Thank you very much for your attention.
Yeah, thank you very much also, Itto. I have just a very short question regarding the experimental plot.
Yes.
There was a very large range of diffusivity. Actually, is this one? No, I think it was another one.
This one?
Is this in different places in the cell? I don't understand. Are the different cells? Or the one you showed, this one?
This one? Yeah.
Yeah, is it? Why can it be different in one cell? Is it in different places in the cell that you have different diffusion constants?
The diffusion coefficient was measured in different local area of the cytoplasm.
Okay. So
yes, so the diffusion coefficient fluctuates over the cytoplasm.
Okay, so where you measure in the cell makes a huge difference. Okay, thank you very much. Then we are coming to the, to the conclusion of the session. And let's thank all our speakers again. And
thank you very much.
Leaving you now, and as a host, Pulcho Sando will take over and guide you through the rest of the next part of the program. Thank you very much.
Okay, thank you.